All right, so chapter 11, statistical inferences based on two samples. So comparing two samples is a lot more common than just one sample. We can compare a treatment and a control group, like two different groups, and compare them. We can look at their degree of dispersion from the formulas that we use, their location of measures and central tendency. Those words might be familiar from last term as well. And we can see if there's an effect on the outcome of the two different activities. All right, so you want to compare machine A to machine B in a factory, you can do that. You want to compare winter tires to summer tires, you can do that. So these sort of things, a diet versus exercise, and so on and so forth. So lots of things, and just about anything you want to compare with two groups. So because we have two groups, I just want to jump to the picture. There we go. Because we have two groups, we have two populations, not one, but two populations. So you can see here, we have population 1 and population 2. So that means we need to get some little subscripts to keep the X bar straight. We don't have just one X bar anymore. We're going to have two. We're going to have X bar subscript 1, X bar subscript 2, and we're going to have also the standard deviations with subscripts and the size of the samples with subscripts. Okay, so we have subscripts N, subscript 1 and subscript 2. And what we do is we take a random sample from each population, and then we calculate the averages of each. And what we want to do is take the difference of the two. Take the difference of the two means. Okay. And that will tell us if there is a difference between them or not. This is how it's done. So we want to know what's the difference between the true population means, mu subscript 1 and mu subscript 2. And we do that by getting the point estimate. The point estimate in this case is X bar subscript 1 subtract X bar subscript 2. That's the point estimate between the two population means. And the standard error of the difference is all this. This is if we know the variances, right? The variance squared, right? And so if we know the variances, does anyone remember if we use Z or T? Do we use the Z? Is it a Z procedure or is it a T procedure? If we are using sigma, these sigmas here. Anyone remember if it's a Z or a T? Z. Yes, it's Z. It's Z because we know the variances. It's assumed from previous studies or previous information from previous studies and so forth that they already know what the variances are. And again, you can see those subscripts there. The subscripts are right in there. Right? And we put it together, and there is our confidence interval for two samples from two populations. We have the difference between the two means, sample means, and then we have the Z. That's our Z score, right? It comes from, we can get those from our T table. All the tables for this course are already on Brightspace, so we're going to be using them at different times. There's actually 5 different tables that we use. Z, you already know how to use Z and T. And I have videos for how to use all these, but we'll go through them in class as well. But can anyone tell me which Z you would use for a 95% confidence interval? What would be the value of that Z? Anyone? Right, 95% of the sample means will fall in between plus or minus, and it's going to be a number. 2. 2 is a good guess because that comes from the empirical rule, or that that rule that we learned, right? The 68, 95, 99.7. But it turns out if you use the table, it actually ends up being 1.96. Does that ring a bell? 1.96, yeah. So 95% is 1.96. And if you look at the T table, I know we're not using T because we have our variances, the population variances, but this final row here, this last row on our T table, this is the T table that we use. The final row there is infinite degrees of freedom, which is really Z. That's really Z. So if you want a 95% confidence interval, it would be T subscript 0.025, because that means there's 2.5% in each tail. Right, so like if I was to draw this, it would be 2.5% here, 2.5% here, and this would be 95%. This would be 1.96, and this would be positive 1.96, and the T, that corresponds to 0.025. Right, it means the subscript is saying how much is in each tail. So then you just scroll down and you go, this is for the 95% confidence interval. And you just scroll down and you can see right there, it's 1.96. Okay. Let's suppose you wanted a 90% confidence interval. How much is in each tail? How much area under the curve is in each tail? If it's a 90, you would have 10. You'd have 10% divided by 2, so it would be 5%. So this here would be your column for 90% confidence intervals. Right? 90. And so forth. Okay, so that's how you use this table for your confidence intervals. And if it's Z, that's when you know the population standard deviations, you just use that last row. Right? Okay, so we'll get back to the table. Let's keep going though. We have a Valentine's Day, it's coming up. So we want to know if, here's an example, we want to know, do male and female consumers differ in the amounts they spend? A lot of time they do comparisons on this with business examples. They want to know how much money each gender by gender. So let's say the average expenditure in a sample survey of 40 males consumers was $135.67, and the average expenditure for Valentine's Day for 30 females was 68.64, so $68.64. Based on past surveys, the standard deviation for male consumers was $35, and it was $20 for the females. So what did we need to do? What would be the point estimate of the difference between the population mean expenditures for males and females? This is a way to know if there's a difference. And you'll see how these confidence intervals are so useful here as we build towards this. So. All right, what do you think the point estimate would be? So we just do this. X bar, have your calculators ready. We can do males, subtract X bar females, or you can do 1 for males and 2 for females, or vice, it doesn't really matter, so long as you have a subscript for each of them, right? And we just take the difference. So that's going to be 135.67. Subtract 68.64. And we get $67.03. So because I put the males first, and it didn't matter how I did it, but it does now for interpretation, because the males are first, and I subtracted and I have a positive number, that means on average, the men spend $67.03 more than the females. Okay. And we could go, hey, there's a difference, and just stop right there. In fact, that's what a lot of business problems do. They just stop right there, and go, yeah, the men are spending way more on the Valentine's gifts, right? But we could make it more formal. We could stop there and go, yeah. Or we could make it more formal and keep going and build a confidence interval. And so we could formalize this, make it more scientific. So what is the standard error for the difference between the two sample means? I denote this with SE, standard error, SE. And we put all this together like this. Now this was males. And we want to add females. That's an M and a subscript F for you to see. We're going to sub those in. Now we're given all this. We just need to sub this in. So $35 squared. And how many males? We had 40 males. And for women, it was 20. Standard deviation was 20, so we square it because that's the formula. And there were 30 females. That's another reason too, to not just stop with part A and report that as your final answer, because there's more men. So maybe it's being skewed a little by there just being more men in the study. So this standard error will even out it'll standardize the data and even out the playing field. So what do you get for that? So be careful with your calculators that this all stays in the quotients and all within that radicand. You want to make sure it all stays in there. So what's the standard error? Does anybody have a dollar amount? You need a dollar amount for this. Yes. 17? Yeah. Anybody get anything different? I've got something different, but we'll take an average of the class. We can get an average for the standard error here. Anybody have another expenditure and a dollar amount? Yeah. 6.6. 6.6, okay. I get 6.63, yeah. Because we call this an intermediate step, because this number, this $6.63 is going into another formula, the confidence interval. So it's really important in this class, really super important, that you carry at least 2 to 3 decimal places on all your intermediate steps. And you'll see with the first lab, not this Wednesday, but the first graded lab, hopefully you're used to it by then too, that we want to leave your answers with at least 3 decimal places or more, because you can never lose marks for that. You will, though, lose marks if you are cutting it off and only doing 1 decimal and you're cutting it off and then you get to the final. You could have so much rounding error that you could end up with a different conclusion. Okay, so it's really important to carry as many decimals as you can. You want to be that Excel sheet with your calculator. Okay. So that's what I got, $6.63. Could have rounded to more with 0 the next digit. 6.63 was 0. Yeah, so there we go. We're gonna, if it says round to 3, then just add that. And then we can put it all together, have the 95% confidence interval. So we're going to use A. So it's going to be this. So this is for the difference between the two population means mu M and mu F. That's what that means. And so it's going to be X bar male, subtract X bar female, make sure that stays together in a bracket. And then we do plus or minus. What should the Z value be? We should know it off by heart. 1.96. 1.96. Yes. Thank you. And our standard error. Just multiply it by the standard error and you're good to go. So it's going to be equal. We get $67.03 plus or minus. Now our margin of error. Margin of error is 6.6. 6.63. And that's going to equal $67.03 plus or minus. What's our margin of error if we multiply that out? Does anybody have a margin of error worked out? It's what I'm looking for is 1.96 multiplied by $6.63. You have it? Yeah, sure. Yep, perfect. That's what we want, 12. And because again, this is an intermediate step, because I want to get the min and max of this. So I'm going to go a little bit further. Is that okay? 4.8. Is that what you got? 9948 for the decimals. And then that ends up being, if we subtract it, it's going to be $54.04. Two, if I add it, that's a 2. The maximum is $80.02. So this is how we conclude and how we say it. We say, on average, the males spend $54 to $80 more than the females. And we have statistical significance because, not because of the amount, we have statistical significance because it didn't cross over 0. So it's really important to remember, if 0 is in the confidence interval, then there would be no difference between their spending. And in this case, it's not in the confidence interval, so there is a significant difference, statistically significant difference. You just look for that 0. If you have a minimum value that's negative and a maximum value that's positive, then you don't have significance. It means there's no difference between the two populations. Okay? So males spend $54 to $80. I'll just round these off. $54 to $80 on average. More than females. And this is, you got to remember, on Valentine, always tie it back to the data. Sometimes we get lost in these calculations. We have no idea what we're, think of it back to what we were doing. The Valentine expenditures, right? Spend more than females on the Valentine Day expenditures. And since 0 is not within the range or the interval, it's not within the range. Whoa, didn't mean to do that. Therefore, it is statistically significant. So the difference is statistically significant. The difference in their behaviors of spending. Lots of information there. It's a massive, great business example. You could compare 2 different branches or 2 different stores, the Masonville branch expenditures versus the White Oaks, and just think of all the ways you could use these confidence intervals. And you just look for 0. If 0 is in the range, there's no difference, because that means 0, it's possible. It means 0 could be the true difference, meaning there's no difference, right? If you take the difference of 2 numbers and you get 0 or close to 0, then there's no difference. But so it's not in the range here. So because it's not in the range, we have statistical significance, and it tells you a lot that there's a lot more spending happening from the males than females for that particular holiday. Okay. And we will build on this and do 3 populations, 4 populations, 5. What if you had 5 populations? 5 branches from a store. You want to compare all 5 stores. So, and it's done really cool. It actually, we keep building on this, and then we can then do, believe it or not, it all fits together really well like a puzzle, and it all fits in, and we can run regression models. Okay. So here, if we don't know the population variances, we need to use S, right? Instead of sigma. These are the sample standard deviations. And as soon as we do that, we need the T. Now you might be going, T, okay, I have 2 populations though. What degrees of freedom should I use? Because you need a degree of freedom. So the conservative method is what we're going to use. There is an elaborate formula, but it's just too cumbersome when we're using calculators. If you're using Excel, great, but if you're using just a calculator, use this conservative. It's very, very straightforward. You take the minimum of either n subscript 1 subtract 1 or n subscript 2 subtract 1. Right? So if you have a group of 10 and a group of 11, then the degrees of freedom would be 9. That's what you would use for the T value, to get that T value. The critical value, right? Critical value T, right? Okay, so let's do an example. Here we go. Here's a bank. We're going to compare 2 branches of a bank, and we want to look at the customers' account practices. So we're going to see their account balances. Yep, count balances. And so they take a random sample at branch A, 28 customers, right? These are customers, by the way. I'm just going to write that in. So this is customers, right? So there's 28 customers at branch A that they have data for, and they have 22 customers from branch B. And then we get the average from the 28, and you get 1,025. You get the average balances for the 22 customers at branch B, and you get $910. And you also get the sample standard deviation. So this would be X bar 1. This would be X bar 2. This would be N subscript 1, N subscript 2. You could use subscripts A and B. I've seen that lots too. We could have said N subscript A for branch A and N subscript B for branch B, but we can use 1 and 2, right? So we'll say branch A is 1 and branch B is 2. And these are our little standard deviations. So what is our point estimate? So the point estimate is the difference between the 2 averages. Now branch A has a lot more money here in the average, but we'll run this through and see. It's this. And we look at that and we put this in, and let's see what you get. We'll see what the difference is. So what's the difference in the amounts between the 2 branches? Anybody have a? Yes, thank you. 115. Right. And we will see what is the standard error for the difference between the 2 means. Again, I do this the same way. And I'm going to put S here. You'll have access to all these formulas. You just have to know which formula and when to use it. Just like you already have learned to do. And so I'm going to grab those values. 150. And just let me know if I write anything that doesn't agree. It happens. Or if you're not sure why there's a value somewhere, but let's see, what do we get for the cash amount here? We should have a standard error in dollars, yeah,
38.9076.
good. So $38, 9076. It's good to carry, even if it's dollars, that makes no sense, like you would say $38.91, but I like that. I like how we're going 4 decimals because this is an intermediate step, we know those are going into more formulas, right? And this way you don't lose marks at all, but if you just said $38, there's some heavy rounding there, so you want to make sure that to be really as accurate as possible, carry as many digits, and it works really well. So we're gonna do this. So this is for the 2 population means. This would be mu1. If I can write mu1 subtract mu2. That's what we're doing this confidence interval for. And it's gonna be x bar 1 subtract x bar 2. Don't forget to keep them in the brackets. Plus or minus a t. And we want to do this t on how many degrees of freedom? Anybody? And it's going to be a 0.025, comma, how many degrees of freedom? We have 2 groups, yeah. 21, because the smallest group is 22, right, branch B, and we just subtract 1 from it, so it's going to be 21. So the degrees of freedom is the min of 28 minus 1 and 22 minus 1. Which one's the min? It's going to be the degrees of freedom is going to be 22 minus 1, which equals 21. 22 minus 1. And then we're going to multiply that by the SE. And we just plug everything in as we get them. So this is going to be, we're going to have $115. Plus or minus a t. We need to get that t from the table. It's a t 0.025 because that means there's 5%, like 2.5% in each tail, right? Because it's a 95% confidence interval, right? So we want to use this column. So let's see if we can grab that column, 21 right there. This is the degrees of freedom, right? Degrees of freedom. And we want this row 21, and I'm just going to back up. And we want this number right there because it corresponds to the t subscript 0.025, which means there's 2.5 in each tail, right? Is everyone familiar with this table? Yeah, from last term. All right, 2.08. 2.08 multiplied by $38.9076. That's going to turn out to be, let's see if I can grab my calculators and have it ready. So let's do this together, 2.08. I get 34.07. And this is the final step. It's not an intermediate step. It's a final step. 115 plus 2.08 times 38.9076. 195. Yes, what I get 2 from there. And this would be a question now. The next question would be, is there a statistically significant difference in the accounts between branch A and B, and the amounts in the accounts from, is there a significant difference here?
Yeah.
Yes, why?
There's, zero.
Right, zero's not in here. I don't see zero. We go from a positive to a positive. Automatically, we say that the two branches are statistically significantly different. They're just different. So who knows? One might be in a location that maybe it's a new location, this, or just the behavior, right? Just the behavior of the clients are different. Who knows why, but that would be up to the banks to figure out why, but formally writing the test out like this with a, basically it's like a test, it's a confidence interval. And you can formally say that branch A has an average of $34.07 to $195.93 more than branch B. Right, because we started with branch A and subtracted B, so branch A has more because they're both positive. If these two numbers were negative, then we would flip it and say branch B has more, right? So it depends who's you're subtracting from. And zero, as we just mentioned, is not within the confidence interval, therefore we have significant difference. Statistical significance, right? We can see, hey, there's a real difference between these two branches. And so you can see these two examples are really useful. It's two examples of how they are used. As we speak, there's probably somebody, some MBA writing out their confidence intervals for something, right? As many different many different ways to use these confidence intervals. Just think of it, two groups, two independent. They must be independent. They can't be related. That's a different test that we'll learn in a bit from here. Another example, so this is just no context to this. It's just literally try it again, but make this for a 99% confidence interval. Let's try this together. See if you can plug these in with your with this. We're going to use this here as our formula. And it's going to be a T on 0, 0, 5, right? Right. 1, it's going to be 1% divided by 2. And then we're going to have our standard error. Our standard error, by the way, is calculated here. We can get all this. This is going to be 2.5 squared over 20 plus 4.8 squared over 30. So try to work this out and see if we can find a minimum and a maximum for this. And then also see if there's a significant difference between sample A and sample 1 and sample 2. I'll do it along with you. All right, so we just go 1.0395, right? And then we're gonna plug those in, so we could go, this equals 22.5, subtract 20.1, make sure they stay together. Plus or minus, what should the degrees of freedom be here? Degrees of freedom. So this is your N1, this is your N2, this is your sample mean, this is your sample mean. Right? So what degrees of freedom, what should I use? Yeah. Is that the T value or the degree of freedom? The T value, so what degree of freedom? The degree of freedom? 19, yes. 19 because 20 is our smallest value, subtract 1, we get 19. So we're going to go in this row right here. And we're going to get, we want 0.005. Now someone said it. Is this what you said? 2.861? Is that what you have? Is that the value? It would be 2.861. Good. Yeah, 2.861 because we're doing a 99% confidence interval. And this is the 99% column. So 2.861. That 2.861. Multiply that by our 1.0395, and we're going to end up getting 2.4 plus or minus. I'm going to get the margin of error in here, 973. Let me just make sure. 2.861 times 1.0395, 2.974, which equals, we're going to get a minimum here. Anybody have a minimum value? Yes. Yeah, negative 0.57.
Oh, it's still 5.37.
Is it 74?
Yeah.
Yeah. 574, thank you, that's good, perfect. 2, so that was a negative number. 2, it's gonna be a positive. It's gonna come to 2.4 plus 2.974. 3 or 5, it's going to come to positive 5.374. Right? That's our confidence interval right there. So the next question I'll ask is, are they different? Is there a difference between sample 1 and sample 2? A significant difference? No, exactly. There's no difference because 0 is a possibility. 0 is in the range, which means any number between negative 0.574 to 5.374, any number which includes 0 can be a possible value for the true difference. And if the true difference could be 0, then that means there's no difference between them. So we have no significant difference here. And in this case, if you end up with a negative and a positive, 0's in the range, then we have no difference. And that's how you would conclude there's no difference. Right? Good. Okay. So I have a video that so that I don't like waste a whole bunch of time, but there is a video for you to watch that shows what if the variances are equal, meaning not exactly equal, but if they're close. If they're equal, then we use what is called the pooled variance. And if this is a different formula, it's called the pooled variance, and you use it, well, for this course, you use it when you're asked to use it. Or if it passes this criteria. So right here, if the standard deviation from the first sample divided by the second sample, right? If that little formula, if that quotient is between 0.5 and 2, then go ahead and use that formula. Go ahead and use the pooled variance formula. That's this one here. If it's not, then don't use the pool, because it means we only can use this formula. We can only pool the variance when they're close in size, so between 0.5 and 2. Okay, and so I give on the videos, under the videos in the thing, I give an example. Right? Right? I just go through an example. That's the only difference. Degrees of freedom, though, for the pooled method is you add the two sample sizes together and subtract 2. Okay, so that would be on your formula sheet too. So remember that. It's basically the denominator. It's the denominator of the pooled formula. Okay, so that would just plug in. You would have everything you need. You would know your standard deviations, you have your n's, you have your x bars. It's just literally, the only difference is just using this formula instead. When the variances are close in size, so right here. Okay, or if I specifically say use the pooled method. So remember how I said at the beginning of the lecture, there's some questions to do for the practice questions, and I have them all listed in the PDFs and all their solutions. There's going to be an example for sure, at least one with and without the pooled method. One with the pooled method and one without. So without the pooled method, it's all these. This is the non-pooled method right here. And this is usually what we use in the real world, is the non-pooled, because we don't usually use the pooled variance because it can be risky if you're not quite right, or if your sample has got a bit of variability and stuff. It's just if you're just not sure, you always default to this. This is the main one. But it's still good to know what the pooled method is, because you may come across it. And then you go, what is that? I don't remember that. So you will now remember because we've covered it, okay? So it's the pooled variance method right here. And it's just basically, it's pooled, it's putting together, it's aggregating it into one little metric. That's why it's called pooled. It puts the two of them all into one little S subscript P for pooled. Okay, that's what the little P stands for, subscript. Right. Yeah.
Okay, so instead of using that one up there, use one for.
So this here, you would take, this one here is square. So you would find it, and then you would take the square root of it. And then sub it in. Yeah, so you would take the square root of this one, the second one, the S subscript P squared, because that's the variance, that's the pooled variance. That's the actual pooled variance, but the formula says just give the thing. So really what you're gonna do is if you have this, you sub it in, but just make sure you take the square root of that as well. Okay? Right. Good. So that's covering everything for the differences.